Hey everyone, welcome to Calculus Remote. This is going to be a discussion of sections 3.6 and 3.7. Specifically, we'll be looking at inverse trig functions and their derivatives. Okay, so first off, let's remind ourselves what the deal is with inverse functions. So one way of looking at inverse functions is a function and its inverse have the same values for their input and output, but just swapped. So the input of the one is the output of the other, and vice versa. So recall, inverse functions swap. Input and output values. So if f of x equals y, that's the same thing as saying f inverse of y equals x. So specifically, these two equations are the same thing. They're just looking at each of the variables as, in this case, x with input, y with output. In this case, y with as input, x as output. So those are that's the fundamental relationship between functions and their inverses. Now let's look at what the inverse trig functions are. So specifically, we're going to look at the three main ones, which are sine, cosine, and tangent inverse. So let's just look at what their deal is. So function input and output. So specifically, so here, to talk first about sine inverse, also known as arcsine. The input is going to be the value of the sine function. So that's going to be in -1 to 1. And the output will be the angle that has that sine, and that's going to be in -pi/2 to pi/2. So you give it the sine value, it gives you the angle. Cosine inverse, or also written arc cosine, is the same thing but with cosines. So the input will be the value of the cosine function that's going to be again in -1 to 1, all the possible things that cosine might equal, and the output will be the angle that has that cosine, and that's going to be in here now 0 to pi. So here, this one, if we're looking at it in terms of the unit circle, it's giving you the angle from quadrants 4 and 1. And here, if you're looking at this one, it's going to be the angle that is in quadrants 1 or 2. Alright, and then finally, the tangent. So tangent inverse, or arctan, just two different ways of writing it, two different names for it. So this will be the value of the tangent function and this is going to be in negative infinity to infinity, so in other words, anything. And the output is going to be the angle that has that tangent value and it's going to be in negative pi over 2 to pi over 2. This time it's not included. On sine it was. This time it's not. Okay, so these are going to be the three main ones that we're going to look at. Now, how do we find the derivatives of these types of functions? Finding the derivatives. Of these functions. Okay, so here's going to be the approach. So first off, we'll look at it like this. We'll start with f inverse. So this will be either sine, cosine, or tangent inverse, as the case may be. And now, in here we'll go the value that represents the output of ordinary sine, cosine, or tangent, but now is the input because we're in inverse land. And the result is an angle, so we'll call it theta. Alright, now, what we can do is set up the inverse function. Or sorry, the inverse equation. So that would be back to original f. And that's going to look like, now f of theta equals x. Now this is something that we could actually try to take a derivative of, because now we are talking about a function that is sine, cosine, or tangent, each of which we know the derivative of, and so we can then we can differentiate both sides with respect to x, which means it'll be an implicit differentiation. That's right, implicit differentiation, our new friend. So after that, we can differentiate both sides implicitly. Implicitly with respect to x. So what's that going to look like? It's going to look like on the left side it was f of theta, so now it's going to be f prime of theta. But if we're differentiating with respect to x, then that means we're going to need to go times d theta dx. On the right side, that was just x, so then when we take the derivative of that with respect to x, it's just going to equal 1. And so then we can solve for d theta dx. So now theta, remember, is the output of the inverse function, so we can think of d theta dx as being the derivative of it. And so what that means is what we're going to have is d theta dx is equal to 1 over f prime of theta. Now that's all well and good, except that this does not involve x, it involves theta, which is not our actual variable that we're supposed to be getting our formula in terms of. It doesn't do much good for me to say that the derivative of arc sine with respect to x is 1 over the derivative of arc sine. That's circular, so it's not going to pay off in the long run unless we can find a way to rewrite theta in terms of x. So specifically, what we can do is take the expression here, and this will be some combination of sines, cosines, or secant squareds, things like that, and we can set up a triangle. This is called a reference triangle. To represent f prime of theta and solve it for x, or solve it, I should say, and then express it in terms of x. We'll see what this means when we actually try it. Okay, so let's actually go ahead and try this. We'll start with the sine. So the sine inverse is going to be our first target here. Our goal number 1. Oh, by the way, the triangle that we're going to be looking at is going to look a little something like this typically, where we're going to have a theta here. We're going to make the hypotenuse 1 for our own convenience. And then over here, we can just call that z for the time being until we have something more explicit to put in there. All right, so let's try this. So first off, sine inverse. So the goal is we want to find the derivative of sine inverse. So let's just start off by setting this up with sine inverse, and here, just because sines and cosines have definitions based on x's and y's, it's useful if we switch our letters around a little bit, and we'll just call it z equals theta. Okay, so this is the equation that we'll be using as our starting point here. But it is not convenient for us because we don't actually know the derivative of arcsine yet. So what we can do is rewrite this as sine theta equals z. So specifically now, so this would be, for example, that triangle is an example of what it might look like. Okay, so now what we can do is take the derivative of both sides with respect to z. So this is going to be the derivative of sine is cosine. And then what we're going to have here is going to be the derivative of theta with respect to z. On this side, I'm just going to end up with a 1. So that's nice. And so then d theta dz is 1 over the cosine of theta. Alright, so this is what it means to say f prime of theta. So you get an actual expression like this. Now if we look at a triangle to reflect this original relationship, sine of theta equals z. Well, sine is opposite over hypotenuse. So if that's theta and the hypotenuse is 1, and z here, this reflects this triangle. Now, if I want the cosine of that very same angle, then that means I need this adjacent side. So this is going to be what we are going to be putting down here. So in order to find the value of that, what I need to use is the Pythagorean theorem. So a squared plus z squared equals 1. A squared equals 1 minus z squared. And then that means that a equals the square root of 1 minus z squared. So this is what's going to go down here. So specifically, we have a triangle that represents the original sine relationship, and then we solve for the side that we need in order to actually put this in terms of something more useful. So what that gives us is then d theta dz is equal to 1 over, and as we just found, 1 the square root of 1 minus z squared. You may be thinking, oh, but what about plus minus situation? So one thing about this a here is that it is referring to an angle that is a possible output for sine inverse, and so that means it's going to be an angle between negative pi over 2 and pi over 2, and the cosine of any such angle is going to be positive. So that means we don't have to worry about the minus situation, it's only the plus situation. So the takeaway here, so the derivative with respect to, and now I'm going to write it in the more customary letters of x, of sine inverse of x, this is just equal to 1 over 1 minus x squared, the square root of that. Okay, so now we have that formula. So I'm using z here. So let's make a note of that off to the side. So note we used z to avoid unit circle confusion. X and Y have a bit of baggage as letters when it comes to the coordinates on a unit circle, so we don't want to let ourselves get confused. If I said sine of theta equals x, you might be confused because that is in fact what that is in fact supposed to be sine of theta equals y if we're talking about standard unit circle setup. So what that means is I wanted to switch the letters for making the formula so that we wouldn't get tricked. But x is by default our letter that we use as the default input of a generic function. So that's a little bit confusing, a little bit weird, but it's what we're doing, so deal with it. Okay, now let's try it again for cosine. So for cosine inverse. So once again, the setup here is that I want cosine inverse of some mystery z, or some input z, to equal the output of theta. But the output of the inverse function is the same as the input of the original function, so I can rewrite this as cosine theta equals z. And now I can take the derivative of both sides of this with respect to z, and so I'll have negative sine theta times d theta dz is equal to just 1 on this side. So then I'm going to have d theta dz is equal to negative 1 over sine theta. And now I just need to set up a triangle to help me figure out what this is in terms of actually the real variable here, which is z. So here from this setup, what we can do is we just need to set up a triangle whose cosine, the cosine of this angle is z. Now what's cosine? It is the adjacent over hypotenuse, so a good example of this would be z and 1. So then the question is, what is this other side, which I'll just call b now, to avoid overlapping with what we were saying before. So then we can use the Pythagorean theorem again and say b squared plus z squared equals 1 squared, but 1 squared is just 1. So then that means that b squared equals 1 minus z squared. And that means that b is again equal to just the square root of 1 minus z squared. I don't have to worry about plus minus once again because the triangle we're talking about here is it reflects the inverse cosine, and the inverse cosine is going to be always giving you an angle that is between 0 and pi, and that means that the sine of that angle is always going to be positive. So we don't have to worry about the plus minus situation. But what that means is then d theta dz is equal to negative 1 over the square root of 1 minus z squared. So the takeaway here, is the derivative with respect to x. Now again, we're just going to default to the generic input letter of x and just express our formula that way. It's going to be negative 1 over the square root of 1 minus z squared. By the way, notice that this fits the general pattern of functions in functions derivatives compared with their with their co-functions. If I told you that a function had such and such derivative, then the derivative of its co-function is negative of the co-function of the original derivative. So here, the cosine and sine, their inverses just become negative after the derivative. Okay, what else do we have here? We have the tangent inverse. Cosine inverse. There. Just wanted that one to be a little bit more distinctive. Okay, tangent inverse. Tangent inverse. Okay, once again, what are we looking at here? We're looking at tangent inverse of our just generic letter z here is equal to theta. Well then, what that means is that tangent of theta equals z. So now I can take the derivative of both sides of this implicitly with respect to z, and the derivative of tangent, we remember, is secant squared theta times the derivative of theta with respect to z, and that'll just equal 1 once again because that's just a z over there. So d theta dz is equal to 1 divided by the secant squared of theta, which you'll notice is actually just the same thing as cosine squared of theta. Okay, so here now, for this one, if I want to set up a triangle that represents this angle, what I can do is create a triangle where the theta's here and the tangent of it equals z. Well, what's tangent? It's opposite over adjacent, so it's going to be z over 1. And so then, if I want the cosine of this angle, I just need the hypotenuse here. So the hypotenuse on this is going to be the result, once again, of the classic Pythagorean theorem. And so what we get is 1 squared, which is just 1 plus z squared, equals h squared. And now what that means then is that h equals the square root of 1 plus z squared. Now what is the cosine of theta going to be? It's going to be the adjacent over the hypotenuse, so it's going to be 1 over h. So it's 1 over square root of 1 plus z squared. Which means then, if I want the cosine squared, I just square this. And so then bye-bye square root, and what we have is 1 over 1 plus z squared. Theta dz, d theta dz. So the takeaway here, once again, we can just sum it up as a formula. The derivative. Now we'll default back to our generic input of x of tangent inverse of x is equal to 1 over 1 plus x squared. Okay, so now what does this mean as far as actual practice? Well, in actual practice, now we have the formulas. We've got oh, sorry, this is supposed to be an x up there. Probably all saw it, but I didn't, so that's an x. Okay, so what that means then is now that we have the formulas, we can just apply all the usual rules of differentiation to these with these as the ingredients of, say, the chain rule, the product rule, what have you. So as an example, let's say I wanted to differentiate the following. Let's say differentiate a tangent inverse of x squared. Well, I now actually have a formula for the tangent inverse, so I can just go ahead and use that, and here we'll have a chain rule action because we have we've got a chain of pieces. So let's just see how this plays out. So the derivative with respect to x of the tangent inverse of x squared is going to be, first off, the derivative of inverse tangent, or arctangent, which is just going to be 1 over 1 plus whatever is under my finger now, squared. What's under my finger? X squared. Times the derivative of whatever was under my finger, so that's going to be times 2x. So what's that equal to? It equals 2x divided by 1 plus x squared squared, which is x to the 4th. And just as another example, if I wanted to do the derivative of the arc sine, so just remember these are also just alternative pieces of notation for the same functions, arc sine of the square root of sine of theta. So now the variable is theta, so the derivative with respect to theta of arc sine square root of sine of theta. So first off, this is probably going to be easiest treated, as square roots typically are in calculus, as a 1/2 power. But first we have to take the derivative of the outer part. So that's going to be the derivative of arc sine, which, as we just found out, is 1 over the square root of, and then down here goes 1 minus whatever's under my finger squared. What's under my finger? It was square root of sine. So be it. Then times the derivative of whatever was under my finger. But it looks like we've got some more chain rule action, so we've got a square root, which means a 1/2 comes down. So we can also think of this as, remember, arc sine of sine theta to the 1/2 power. Okay, so that'll make it a little easier for us to do the differentiation. So then what's that going to be? It's going to be sine theta to the negative 1/2. And are we done? No, we aren't, because this is more chain rule. This was square root of, not just theta, but sine theta. So then times also the derivative of sine theta, which is cosine theta. So let's see if we can clean this up a little bit. So what do we have? We have 1 over square root of 1 minus, well, we have a square on top of a square root in here, so that's going to just become sine theta. And beyond that, it looks like there's not a whole lot more that we can hope to accomplish here, since that is really a square root of sine theta. So I'm not gonna push my luck. I think we can just go ahead and call that good. It's a little embarrassing to leave a square of a square root, but beyond that, there's not much else. Not much else we can do that will be of any use to anyone. So this is how we find the derivatives of the inverse trig functions. And how do we use them? Well, once you have the formula, you just use them by ordinary differentiation rules. So the chain rule is in effect, the product rule is in effect, the quotient rule is in effect. All derivative rules are still valid, even for these functions. So that is the derivatives of the inverse trig functions. Alright, now let's take a quick look at section 3.7, where we will finally be seriously looking at the derivatives of logarithms. So, the derivatives of logarithms. So first off, recall log base A is the inverse function to A to the power of whatever. Yeah, right. I like this. Also, specifically the natural log is the inverse to e to the whatever. So now what that means then is that we'll be able to apply some of the same sort of spirit to this as we did to the inverse trig functions, in that we'll set up an equation, we'll rewrite it the other way, and we will and then we will be able to hopefully solve for the derivative that we want. Now here specifically, what I want to do is also recall one other thing, one other fact. A to the x is the same as e to the natural log of a times x. Okay, these are the three facts that will be useful to us in the course of our investigations. So first off, first goal, we just want to take the derivative of just a general logarithm. So we'll set up an equation. So we'll set up log base A of x equals y. If these are inverses, and they are, then we can rewrite this as a to the y equals x. But I can rewrite that as e to the natural log of a times y equals x. And now I can differentiate with respect to x, so implicitly and so what's that going to give us? Well, natural log of a is just the base, so it's just a constant. So I'll just treat it the same way I'd treat like a 5. So what do we have here? We have e to the blank. So the derivative of that is just going to be e to the blank. But then times the derivative of the inside with respect to x. So that's going to be a constant still, just coming forward, times dy dx. On the right side, what do we get? We just get a 1, because we're differentiating with respect to x, so the derivative with respect to x is just 1. But what's this over here? This is just the same thing as a to the y times ln a, and then that's still times dy dx, and that equals 1. Okay, so then if I solve this for dy dx, then I'm just going to have 1 over a to the y natural log of a. But what's a to the y? That is just the same thing as x over here. So we have 1 over x times ln a, which we can rewrite as 1 over ln a times 1 over x if we want, or however we want to write it. Okay, so now the takeaways. So the derivative with respect to x of any old logarithm is 1 over the natural log of the base times 1 over x. And in fact, if the base is e, then that means that we don't even have to worry about this extra little factor. And so more specifically, the derivative with respect to x of the natural log of x is just going to in fact be 1 over x. Alright, now let's try putting that to some use. Now, one of the great benefits of logarithms is that they can sometimes lead to some very nice properties when it comes to evaluating things, and they can also have some nice benefits for differentiation, because when you differentiate things that are broken into simpler pieces, that's going to be a lot easier to work with. So, just as some examples here, let's differentiate a bunch of things and see what happens. So differentiate the following. Alright, first one, we'll just go with a nice little chain rule here. Just say f of x equals ln cosine x. Alright, so to take the derivative of this, we will just use the chain rule. So f prime of x is equal to derivative of the outside, which is 1 over, and then you put the inside in, times the derivative of the derivative of the inside, which is just going to be negative sine x. So it's just chain rule. You just go log of everything under my finger. So then that's the derivative of the log becomes 1 over whatever was under my finger times the derivative of whatever was down there. And so what does this equal? Negative sine x over cosine x, which actually, you notice, we can rewrite as just negative tangent of x. Okay. Well, that's not too bad. How about something like this? B. What if we have y equals, let's say, the natural log of x squared? And by the way, even if these parentheses weren't written here, it would still mean the same thing. The square just by default applies to whatever is next to it. Okay, so now what's the derivative of this? So dy dx is going to equal, well, once again, well, actually, before we do this, whoa, let's just think about this for a second. We've got a logarithm here. Logarithms have their own properties. We don't know much about the properties of the logarithm of the cosine of something, but when it comes to the logarithm of an exponent, that is a known quantity. So remember, the properties of logarithms that we can use here would be that this power can come out to the front. So we can rewrite this before we even start the calculus part of it. So now we're ready to start taking the derivative. So the derivative with respect to x of y is now just going to be 2 times 1 over x. Or in other words, just 2 over x. Okay. Well, is the same thing true if I have something that looks like this? Let's just say now it's g of x equals the natural log of x all squared. Same rule? No. Very different. Very different, because this is taking the overall outcome of the natural log and then squaring that. So it's not the same thing as squaring the x first and then taking the log of that. So if I want to take the derivative here, I once again have to use the chain rule. So down comes a 2. And then we have whatever it was that was inside here, natural log, to the power of 1, times the derivative of what was in the inside, so now times 1 over x. So that's a power of 1. So then that's, in other words, 2 natural log of x, all divided by x. Okay, well, so be it. Alright, how about something like this? D. What if I wanted to take the derivative of the natural log, so I'll say y again, the derivative of the natural log of, and now inside this, on the top we're going to have the square root of x minus 1, on the bottom we're going to have the square root of x plus 1. Well, if we were not thinking things through, we might just roll up our sleeves and get ready to differentiate. But a couple steps into that, we would be kicking ourselves because this is about to spin way out of control, become way too complicated. We're gonna have to use the quotient rule or some other such thing once we get to that level of the chain. So first things first, let's just apply some of the magic of logarithms to see what we can do to make our lives a little bit easier going forward. So first off, whenever you have the logarithm of something divided by something, that's the same as the logarithm of a minus the logarithm of b. It's a property of logarithms that's true for any base, and in particular for the natural log. Okay, so then if I use that, then it's going to be the natural log of x minus 1 minus the natural log of square root of x plus 1. But square roots, we don't like square roots when we're doing calculus, but we also don't really care for them when we're doing logarithms. Whenever we can, we will change them to fractional powers. And so then down comes the exponent according to one of the other celebrated laws of logarithms. So this is now 1/2 natural log x minus 1 minus 1/2 natural log x plus 1. Okay, so that's as far as logarithms can take us without doing any calculus yet. We haven't taken any derivatives. All we've done is rewrite things using the properties of logarithms. Now if I want to actually go about taking the derivative of this with respect to x, I have two relatively simple pieces to work with, which is much better than what I started with. So it's going to be 1/2 times 1 over x minus 1, and then courtesy of the chain rule, I'd multiply by the derivative of the inside, but the derivative of the inside here is just going to be 1, so I won't even bother writing it. Minus 1/2, and then again, chain rule is in effect, so first off 1 over everything that's inside there, and then times the derivative of everything that was inside there, but again that's just going to be 1. So there we have it, 1/2. 1/2 times 1 over x minus 1 minus 1/2 times 1 over x plus 1. So by using the properties of logarithms shrewdly, we were able to avoid a lot of what was about to make this problem very messy. Alright, we've been harping on the natural logarithm a lot, but there are other logarithms out there, and most commonly you would see log base 10 or log base 2 as alternative logarithms. Let's see what it would look like if we went about one of these. So say h of x is equal to the log log. Also we could write it as log base 10, which we will here, but often it's just written log log. So log base 10 of tangent x plus x. Well, unfortunately, the laws of logarithms help me if I am multiplying together two things, if I'm dividing two things, if I'm raising something to an exponent, but they have nothing to say about an addition of two things. So unfortunately here, I am not going to be able to use the magic of logarithms to rewrite this in any way, because it is just first and foremost an addition. So we just gotta roll up our sleeves and start differentiating. Okay, so now what we have is a log of blank, and that's the log base 10 of blank. So log base 10, the way to deal with that is it's 1 over the natural log of 10, which is just a number, and then times, now 1 over blank, so that's going to here be tangent x plus x, but then times the derivative of blank, so times the derivative of what was on the inside. So what's that going to be? Secant squared for the tangent, and then plus 1 for the x. So if I put the pieces together here, what do I have? 1 over natural log of 10 times, and here I'll just write it like this, secant squared x plus 1, all divided by tangent x plus x. So the properties of logarithms didn't help me there, but here they helped a lot. So always keep your eyes peeled for the properties of logarithms and how they might help you make things a little bit simpler. Note. So this is something that you'll see more in Calc 2 than you will here, but it is just a fact that is worth noting. The logarithm, so let's see, so note. So the logarithm is very particular about the kinds of inputs it allows. It allows positive inputs and positive inputs only. Not zero, not a negative number, only positive values. So here specifically, that does restrict what you can put into a logarithm pretty heavily. But you can loosen things up a little bit if you say take the logarithm of the absolute value of x instead of just x. Now if you do this, actually, the results of taking the derivative of this expression is actually the exact same as the result of taking the derivative of just regular logarithm, and it will still just equal 1 over x. So it's just a fact. It will come in a lot of handy for you later on in life, but not so much, again, as I said, in this class, as it will in classes to come, namely Calc 2. Okay, well, I can't help but turn back to examples B and D here when doing a little bit of preliminary logarithm work really seemed to help me out. Now it turns out, actually, you can get some of those same benefits by actually doing a logarithm to an expression that didn't already have one. So here's what this looks like. So this is called logarithmic differentiation. So here's the setup. We want the derivative of f of x which is a complicated expression but which could be simplified if we took the logarithm of it. If we took its logarithm. Say ln. So if we took its natural log. So here's the way we do it. So the process. So right, y equals f of x, then apply ln, so we have ln of y equals ln of f of x, and then hopefully now we'll be able to do some useful simplifications. Simplify the expression. Then differentiate both sides implicitly. With respect to x. So then we're going to have 1 over y times dy dx, chain rule in the version of implicit differentiation. Then over here we're going to have 1 over f of x times the derivative of f of x. So since this right side is already in terms of x, it doesn't require any extra implicit differentiation steps. It's just going to be the chain rule. And then we just solve for dy dx. And we can replace y in the result. By the original f of x. Because after all, y was just what we were calling that. Alright, let's try an example. So here's an example of a function which may not look so bad until you really dig into it. So a. Let's say y equals x to the x. Alright, so first off you see an x in the base and you think, oh, maybe I can do the power rule. But then you see an x in the exponent and you say, whoa. Whoa, whoa, whoa. This is neither a power function nor an exponential function, but it's some weird combination of them both. So, that's weird. What are we going to do about this? Well, whenever you have an unsightly exponent which you wish didn't exist, you can't help but fantasize about what if there had been a natural log there. So now let's actually see what that would give us. So natural log of y is equal to the natural log of x to the x. And what is that going to do? That's going to be natural log of y is equal to x ln x. Well, that's more like it. Now that looks like the kind of function we know how to deal with. So now let's deal with it. So we take the derivative of both sides. And what's going to happen is that we are differentiating implicitly, so it's going to be 1 over y times dy dx. And on the right side, it's not going to be implicit, but we are going to have to do the product rule here, though. So now product rule says derivative of the first. It's going to make it just ln x. And then plus, leave the first alone, times the derivative of the second. So then where does that take us? Well, it looks like it's 1 over y dy dx is equal to the natural log of x, and these two actually just cancel and just make 1 plus 1. So now if I want to solve this for dy dx, all I have to do is multiply both sides by y. Oops. This happens when you write and talk at the same time. dy dx. Multiply both sides by y, so it's going to be y ln x plus y. But wait, what was y? Y was just x to the x. So the ultimate result here, dy dx, just put that back in, x to the x times ln x plus x to the x. Well, that was a function that we didn't even have the slightest idea how to do in its original form, but after taking the logarithm, all of a sudden things presented themselves in a new light. Let's try one that looks like looks even weirder, but is actually very similar. So, even weirder looking, we might have something like this. What if y equals, so at first you might think I'm about to write the square root of x, or maybe even the cube root of x. But what if we did the x root of x? So what is that saying? Like if x is 2, then it's the square root of 2. If x is 3, then it's the cube root of 3. If x is 4, then it's the fourth root of 4, and so on. So you can see what this kind of means, but it's a strange looking function, and one that we have no way of taking the derivative of by any of our normal rules. Alright, well, first off, if I'm going to do anything with logarithms or derivatives, I'd rather see an exponent rather than a root, so I'll rewrite it as x to the 1 over x. And now if I take the logarithm of both sides, then I'll have ln y is equal to ln x to the 1 over x. And now the properties of logarithms come to the fore, and we have 1 over x ln x. And on this side we have ln y. And now we've gone as far as the logarithm train can take us, but the derivative train is just about to leave the station. So now we take the derivative, we differentiate both sides, and we're going to have 1 over y dy dx, because we're differentiating, as always, implicitly with respect to x. And then on this side, what are we going to get? We're going to get, so the derivative of 1 over x is, here, maybe I'll even rewrite this one more time, as x to the negative 1 ln x, just to make things easier on ourselves. So down comes the exponent, and then x to the negative 2 ln x. And then plus the derivative of the second. So x to the negative 1 times 1 over x. But wait, 1 over x is the same as x to the negative 1, so this is actually x to the negative 1, x to the negative 1. So it's going to be, all together here now, negative x to the negative 2 ln x plus x to the negative 2. Well, that's what 1 over y dy dx is. So if I want to get dy dx itself, I just have to solve for that, and I do that by multiplying both sides by y. So then dy dx is going to equal, so it's just going to be negative, I'll just write it like this, y x to the negative 2 natural log x plus x to the negative plus y x to the negative 2. But what's y equal to? It's the xth root of x. So what's that look like? It's going to be negative x root of x times x to the negative 2 natural log x plus x root of x to the negative 2. So there we have it. You could rewrite this all as powers of x if you wanted, but what's the point? It's not going to help anything. So we can just go ahead and call that a successful differentiation of a function that we had never even dreamed could exist up until just a second ago. So once again, the process of logarithmic differentiation, you start by writing it out, then you take the logarithm of both sides, which you then differentiate implicitly with respect to x, and then you solve for dy dx. Alright, seems pretty roundabout, but it can be quite useful. Alright, well, this has been Snow Day edition of Calculus. I hope everyone is warm and safe, and I'll see you next week. Till then, bye.